Hello from London. My name is Fiona Walport and I am a Research Associate at Imperial College London, and today I will be presenting our work on equivalent bow imperfections for design by second order inelastic analysis with co-authors Prof. Leroy Gardner and Prof. David Nethercot. I will begin with a brief introduction on equivalent imperfections and the shortcomings of the current provisions for application with design by second order inelastic analysis, followed by the development of our proposed imperfections and the parallel reliability assessment, and finally some conclusions. So imperfections inherently occur in manufacturing and fabrication of steel members, as well as during construction of structural systems. Therefore, it is essential that they are included in the structural analysis to allow for their influence on the load carrying capacity in design. For frame structures modelled using beam elements, there are two main types of imperfection to consider, and these are geometric outer straightness and residual stresses. But modelling residual stresses can present challenges to a designer, and the effects of both of these can instead be considered through the use of equivalent bow imperfections as provided by the Eurocodes. In the upcoming Eurocode 3 Part 1, these imperfections can be calculated following two approaches, either through back calculating the imperfection or more simply as a fixed proportion of the member length using tabulated values. The latter imperfections are calculated as a function of the imperfection factor alpha, which allows for the varying influence of residual stresses, epsilon, which accounts for material strength, and beta, which really takes into account the differing spread of plasticity for different types of axes of buckling and different cross-section types. Both approaches require a further cross-section check, and both have been derived based on the assumption of linear elastic behaviour. So for stainless steel in Part 4, no further provisions are provided, and consequently the carbon steel rules are assumed to apply. The tabulated equivalent imperfections apply equally to cold form steel and stainless steel members, provided the appropriate value of imperfection factor alpha is employed. While for the back calculated imperfections, due to the limiting slenderness in the stainless steel buckling curves not being a constant value, a small modification is required as shown. This slide illustrates the application of the back calculated imperfections with a second order elastic analysis. It can be seen that the resulting column buckling resistances are the same as those obtained from the European buckling curves. Use of the elastic back calculated imperfection results in a force moment path that directly intersects the linear elastic interaction surface exactly at the Eurocode buckling resistance of the column. Likewise, if a linear plastic cross-section check is assumed, use of the plastic moment capacity results in a larger imperfection, and the force moment path intersects the linear plastic interaction surface exactly at the Eurocode buckling resistance of the column. This imperfection is larger to compensate for the loss in stiffness due to material nonlinearity that would occur in practice beyond the point of first yield, but is not captured in the elastic analysis. The same theory applies with the tabulated imperfections, with the values intended to approximate the back calculated imperfections while remaining safe-sided and reducing the complexity of the calculation by avoiding the dependency on slenderness. As previously mentioned, these imperfections have been derived on the basis of second order elastic analysis, and no further provisions are currently given for use with inelastic analysis, where the influence material yielding is directly captured in the analysis. In general, it is not appropriate to use the same imperfections for inelastic analysis due to the effect of plasticity being partially duplicated. To illustrate this point, in these figures we can see that utilising the back calculated imperfections derived for the elastic cross-section check as an example can result in both overestimations and underestimations of system strength depending on the material response considered. In the case of hot rolled steel, no allowance is made for the post-yielding strength, and utilising the current imperfections would result in an unsafe prediction compared with the buckling curves. Conversely, for stainless steel, the early material yielding results in a conservative result. Thus, new equivalent geometric imperfections suitable for use in design by second-order inelastic analysis are required. Equivalent bow imperfection amplitudes were therefore sought such that the peaks of the force moment curves obtained from inelastic analyses aligned with benchmark ultimate loads. Now, the benchmark ultimate loads were calculated using second-order inelastic analysis with a geometric imperfection amplitude of member length L over 1,000, as well as residual stresses. These benchmark FE results were chosen over the use of the existing buckling curves to avoid the unnecessary introduction of errors caused by fitting to results whose accuracy is restricted by the algebraic form of the underlying resistance function. This point is illustrated in this figure, which shows normalised benchmark ultimate loads for hot rolled I sections of 4 different steel grades. It can be seen that the buckling curves become increasingly conservative with increasing steel grade relative to the benchmark FE results. A similar shortcoming is shown in this figure for the stainless steel buckling curves, but this time in relation to changes in the strain hardening exponent N. Although in practice there are different values of N for different grades of stainless steel, the buckling curves are independent of N and therefore give no change in resistance when this parameter is varied. This is, of course, at odds with the real observed behaviour. Therefore, propagation of these systematic mismatches between the buckling curves and the FE data was avoided by using the benchmark FE results as the reference for establishing the equivalent imperfection amplitudes herein. So equivalent bow imperfection amplitudes for use in design by inelastic analysis were derived by iteratively calculating the imperfection to give the same capacity prediction as the benchmark results from the GM and IA with L over 1,000 and residual stresses. The study considered hot rolled steel, cold formed steel and stainless steel, as well as a selection of I sections and hollow sections. Based on these calculated required imperfections, a reference relative bow imperfection beta of 1 over 150 has been proposed for all design cases. The influence of material non-linearity is now directly accounted for in the analysis, and therefore the epsilon term is no longer required, while the imperfection factor alpha still accounts for the varying degree of residual stresses in the different cross-sections. Considering now the reliability analysis. The reliability level and required partial safety factor for use with the proposed equivalent bow imperfections in design by second-order inelastic analysis was assessed using the first-order reliability method set out in EN 1990. The dependency of the column buckling resistance on the basic variables yield stress, cross-sectional area and Young's modulus changes with the member proportions and therefore between each numerical simulation. Hence, for each FE result, the dependency of the resistance, presented as the exponent to which the basic variable should be raised, was determined. So these figures show the values of the exponents for all compression cases considered, and as an example, we can see that as the slenderness increases, the dependency on the yield stress and hence the exponent C reduces, while the dependency on the cross-sectional area and hence exponent D increases. This makes sense because the buckling load approaches the elastic buckling load as slenderness increases, which is a function of the section geometry but independent of the yield stress. The assessment was carried out on 584 beam columns, considering both major and minor axis buckling, 3 slenderness values, 4 ratios of applied compression to bending, and 3 bending moment distributions along the member length. The partial safety factor and the mean correction factor B were calculated for all cases, with the mean correction factor B calculated based on the average ratio of benchmark resistance to predicted resistance. The study concluded that partial safety factors of 1.0 for steel and 1.1 for stainless steel can safely be adopted. Looking at an example now, we can see in this example of a hot rolled steel column that the proposed imperfection in red provides a more precise prediction while remaining safe-sided the benchmark result in blue, calculated from a GM&IA with L over 1,000 and residual stresses. So now for some conclusions. While the revised provisions for equivalent bow imperfections in the upcoming Eurocode 3 Part 1 are appropriate for use in design by second order elastic analysis, their use in design by second order inelastic analysis is not appropriate. Thus, new equivalent imperfections were sought, and following calibration against benchmark finite element ultimate loads generated using second order inelastic analysis with imperfections of member length L over 1,000 and residual stresses, a proposal was made where beta equals 1 over 150 for all materials and cross sections. The reliability of the proposed approach was assessed against the benchmark FE ultimate loads, where it was shown that partial safety factors of 1.0 for steel and 1.1 for stainless steel could be adopted. These imperfections are due to be included in the upcoming Eurocode 3 Part 14 for finite element analysis, and more details can be found in our journal paper with the reference presented on the screen. Thank you very much for listening.